Hey, welcome back. This is 4.3. We want to solve homogeneous linear equations with constant coefficients. So the type of equation we want to solve is that equation 1 there to the right. And we've seen these equations back when we were dealing with linear first order differential equations. It's just now we're going to assume that all the coefficients will be constants. Okay? And we'll be looking at higher degree, not just first order differential equations. But anyways, kind of the motivation, we've already seen it, and your homework in 1.1, believe it or not. Okay, so they were sort of foreshadowing this issue that is coming along today. So in 1.1, we call number, I guess 13 here. Find all values of m so that the function y equals e to the mx is a solution to the differential equation. So we have y prime plus 7y equals 0. And basically, we think y equals e to the mx is a solution. And if you did go through the trouble of separating this differential equation, that would be the case, right? Because you would have y prime equals negative 7y, which is our exponential growth formula there. dy over dt equals, or in this case x, I guess, dx equals negative 7y, and then you separate, exponentiate, et cetera, et cetera. But anyways, you know, the rate of the growth of the population y is proportional to the population. That's our exponent. So we presume that this thing is going to have some sort of solution, y equals m to the x, y equals e to the mx. We could figure out what value of m by taking its derivative. So the derivative of e to the mx is e to the mx times m. Then we could just plug that stuff into that, plug this information into this differential equation. So let's do that. We would get me to the mx plus 7e to the mx equals 0. We could factor this, factor out the e to the mx, and we have m plus 7 equals 0. So m plus e to the mx will never equal 0. There's nothing you can put in for x that would equal 0. So that part never happens. But m plus 7, that would cause this thing to we could find a number m that would cause it to equal 0, right? In particular, m is negative 7. So we think a solution to this differential equation would be y equals e to the negative 7x, right? And of course, if we were to now go back to our differential equation here, we could solve that, you know, divide both sides by y, move the dx over, integrate both sides, exponentiate both sides, and then drop the absolute values. Of course, there you see the e to the negative 7x. This is what we found is just a particular solution. Okay. Then number 14 is a sort of the same deal, and this becomes the way we're going to solve these differential equations. Okay. This thing right here is going to be called the auxiliary equation, and it tells you information about the solution. So anyways, let's look at number 14 as well. 2y double prime plus 15y prime minus 8y equals 0. Again, we want to find the values of m such that e to the mx is a solution. So again, we could go y prime and then y double prime. So y prime is me to the mx, and then y double prime would be m squared e to the mx, just doing chain rule. Plug that information in, so you get 2 m squared e to the mx plus 15 me to the mx minus 8 e to the mx equals 0. Factor out the e to the mx, and you get 2m squared plus 15m minus 8 equals 0. And then you could solve this thing again. This is the auxiliary equation. 2m squared plus 15m minus 8 equals 0. We can factor that, right? it's like 2m and, I don't know, 4 and 2, that ain't gonna work. 8 and 1, really? Okay, so 8, subtract here, plus here, and then just m here. Let's just make sure that works. So I need the other guy to be negative. So this one I need to be positive, that one to be negative. Okay, equals 0. So our m values, so there's 2 possible, m plus 8. 2m equals 1, so m equals 1/2, and the other one, m equals -8. So 2 solutions. These solutions are linearly independent of each other. You could put them into the Wronskian and figure that out, but in general, we'll say the general solution is y equals c1e to the 1/2 x plus c2 e to the -8x. Okay, and that will be a quick way of solving these linear differential equations with constant coefficients. That is the general solution of that differential equation there. Okay, so that's kind of what they go through here in the beginning, and then they introduce the auxiliary equation. So usually we won't do this substitution part right here. What we'll do instead is kind of just jump from this equation to this equation. And you can see all you have to do is replace the y with m squared, the y prime with m, and then just put a 1 on for the y. Okay, once you get that thing, you can get the m values and produce your solutions. Okay. Unfortunately, there are several cases that we have to worry about because, so let's introduce it officially now, the auxiliary equation. I mean, you could have any order differential equation. It's just that finding the roots will become a lot harder. But the book will focus in the beginning on second order linear. So basically ay double prime plus by prime plus cy equals 0. And then the associated auxiliary equation will just be am squared plus bm plus c equals 0. And then we solve this. Worst case scenario, of course, you go to the quadratic formula, so that would be negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And there's, then 3 possibilities for solutions here. The first possibility is you have 2 real roots, and that's the case we saw here in number 14. Okay, so let me entitle that section 2, case 1, 2 real roots. And in this case, your solution y will be c1e to the m1x plus c2e to the m2x. Okay, so let's look at a problem from the homework. Okay, so let's fast forward to 4.3 then. And hopefully we can pick off one of these, sure. So number 4, we have 12y double prime minus 5y prime minus 3y equals 0. Okay, so you form your auxiliary equation, 12m squared minus 5m minus 3 is 0. And then you're just back in algebra land, you're just figuring out how to factor this. 4 and 3, yeah, maybe 4, 3, 9, yeah, so 4, and then sorry, 3 here, and then 3 here should do it, and we want the negative right here, so that'd be m, and then plus 1, I guess. So make sure that works. 12m squared minus 9m plus 4m is negative 5m, and then minus 3. Okay. Solve each factor, set each factor equal to 0 and solve. So we get 4m equals 3, so m equals 3/4. Here 3m equals -1, and then m is -1/3. So our general solution then, y equals c1e to the 3/4 x plus c2 e to the -1/3 x. Okay, so no big deal there. But that's the first case. You have the one, or you have distinct real roots, 2 real roots. Okay, and it's all based on the discriminant, right? So if this thing is greater than 0, you have the 2 real roots. If it's equal to 0, you have 1 root that's repeated, and then if it's less than 0, you have 2 imaginary roots. Okay, so let's look at the second case, which is actually section 3 in my notes, unfortunately. Case 2, and you have 1 repeated root. Unfortunately, I won't be able to show you the kind of why this is true. We would need to do I think it was a variation of parameters section 4.2. We didn't do that, or reduction of order problems. It's not all that important. I guess it's just, there's some mechanics in there. But at the end of the day, what happens is you get sort of like before, c1e to the m1x, and then instead of c2e to the m1x, you're going to tack on an x. Okay, so c2xe to the m, and then that gets repeated, e to the m1x. If you had 3 repeated roots, the next one would be c3x squared e to the m1x, and then the next one would be c3x, or c4x cubed, etc. And we'll talk about those higher order ones here coming up soon. Anyways, let's look at one of these real repeated versions. And you can see number 3 is one of those types. So y double prime plus 14. I mean, I can see it because I can see the answer. I can't just look at it and know. But anyways, this, I guess you can. This is a perfect square trinomial. Is that what they used to call those? But anyways, let's get our auxiliary. So you just do it like you did before. And the issue here is you won't have 2 answers, right? You'll just have one that's repeated. So if you factor it, m plus 7 times m plus 7 equals 0. So m equals -7, -7. In other words, -7 is repeated. So our general solution, y equals c1e to the -7x plus c2x e to the -7x. Okay, the third case then is when that discriminant is less than 0, and then you'll have the imaginary ones. The way to get sort of our final form for the imaginary ones is a little weird. So this is case 3, 2 imaginary roots. Officially, you could just literally plug the imaginary roots into the exponent. So say you have alpha plus I beta x. If you have that as one of your roots, you automatically have alpha minus I beta as your other root. So c2e to the alpha minus I beta x. That is officially the answer, but it's not the form we want. We don't want to have to work with the imaginary numbers. So what we're going to do is take Eulers' formula, which says that e to the I theta is equal to cosine theta plus I sine theta. Okay. You could derive this from a substitution on Maclaurin's series, and I think that's the way you usually do it. But you've probably not seen it before, but hopefully you can just stomach it as it sits. Okay. You may have seen it at the end of like a trig class. Sometimes they show it there. Anyways, we'll use this formula to rewrite that general solution above. So first note, firstly, note e to the I beta x is going to be equal to, from this formula, cosine of beta x plus I sine of beta x. E to the I negative I beta x so I slide a negative in there, is going to be cosine beta x plus I sine of negative beta x. So remember, if you plug a negative into cosine, because cosine's an even function, it just goes away. You can literally just, say goodbye. If you plug a negative into the sine function, so if you have negative beta x, you can, because sine is odd, you can move it out. So remember these identities: cosine of negative theta is equal cosine of theta, and then sine of negative theta is equal to negative sine. It's just trig stuff. Okay. So there's that information. Hence, we could rewrite our solutions. This general solution here, we can rewrite this as y equals, and then there's going to be an e to the, so let me, c1 e to the alpha, e to the I, alpha x I beta x, plus c2 e to the alpha, e to the negative I beta x, and then we could rewrite this junk. Factor out the e to the alpha x. I lost an alpha over there. So we have c1 e to the I beta x, but then I'm going to write the, the cosine beta x and distribute the c1 plus I c1 sine beta x, and then plus c2 cosine beta x minus I c2 sine beta x. I'm running out of room. Sine beta x, and then we can rewrite this a little bit by collecting like terms. So collecting the c1s together and factoring out the c1, I get c1 times. Or actually, I want to instead collect the cosines together. So I apologize. Let me get the cosines together. So c1 plus c2 cosine beta x. So I'm going to factor out the cosine beta x kind of in this way. So I have c1 plus c2 times cosine of beta x. And then I'm going to go and factor out the sine part, the sine beta x from these two terms, along with the I part. So I'll have c1 minus c2i times sine of beta x. Okay. And then there's a corollary way back on page like 121. So there's this corollary that's going to allow us to do a cool little simplification. This corollary A, you click on the hyperlink, it'll go to it in the book, which is pretty cool. But basically, you could take any constant solution of a solution of a homogeneous linear differential equation, and it'll also be a solution. So we can kind of manipulate this general solution, and what I'm going to end up doing is kind of just replacing all of this business with a constant c1, and then replace all of this business with a constant c2. Okay, so you can imagine, regardless of what the constant would be, you can always multiply by something to create this new constant because of that corollary. Okay, and it too will be a solution, and so we'll end up writing our general solution finally as y equals e to the alpha x times c1 cosine x, or beta x rather, cosine beta x, plus c2 sine of beta x. Okay, so let's grab one of those from the homework. We can find one. So there's number 6. Oops. You can see that'd be kind of nasty, like number 7 if you're looking at the answer there. But number 6, we have y equals, oops, the differential equation, y double prime minus 8y prime plus 17y equals 0. Okay, great. So get the auxiliary, m squared minus, so it's just business as usual. You can try to factor it, but it won't work, right? So you have to go to the quadratic. M equals negative 8, which is 8 plus or minus the square root of b squared, so 64, minus 4 times a times c, all over 2 times a, so 2. So that'll be 8 plus or minus the square root of 64, so 17 times 4, 8, carry the 2, 68. So 68 minus 64, of course, is going to be negative 4. So we got to get those two imaginary roots. And so we'll have 8 plus or minus 2i all over 2. And then we could, butterfly this. So we get 4 plus or minus I. The alpha part is the 4. Okay, so the form is the alpha plus or minus beta I, and the beta then is 1. So our general solution, y equals e to the 4x times c1 cosine x plus c2 sine x. Okay, and that's it. Yeah, so this is the important point in this case. So there's basically 3 formulas. Not this one, this is just the introduction, but it's this one that's the one we use. That's our workhorse. And then there's this equation for repeated roots, and then this equation for 2 real roots. Okay. From there, what we need to do is kind of consider repeated versions of all these that come up with higher order differential equations. So section 5, higher order. And let's consider some of the cases that could happen. So basically you could just end up with a whole bunch of different roots. And in that case, your solution would be like c1e to the m1x plus c2e to the m2x, etc., plus plus cne to the mnx, if you have an nth order linear differential equation where all the roots are different, real different roots. Part B, case 2, where you have repeated roots, and we'll say that, let me write that as a number 2, not numeral 2. Let's say that you have k repeated roots. Okay, so k repeated. So whenever you have a repeat, what you're going to do is just kind of tack on an extra factor of x. Okay, so if it came down, you had root m repeated k times, your solution would be c1 e to the mx plus c2 x e to the mx plus c3 x squared e to the mx plus plus c sub k x to the k minus 1 e to the mx. Okay? And I mean, that's really the idea, and it carries over to repeated imaginary roots as well. So case 3, let's say we have k repeated, and this is a little harder to write out, but I'll try. K repeated imaginary roots. With imaginary roots, they always come in conjugates. So let's try this. We have y equals e to the alpha x times c1 cosine beta x plus c2 sine beta x. Then you'll have plus, you just tack an x in there, right? So e to the alpha x times c1 cosine beta x plus c2 sine of beta x, then plus e to the alpha x squared, and of course you could distribute the x squared if you want to. C, whoops, and these should be C2, then C3, or rather C3, C4. Sorry about that. So all of the constants are different. C4, and then this would be then C5, cosine beta x plus C6 sine beta x plus dot 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 plus e to the alpha x, x to the, I guess, k minus 1, again, so k minus 1, and then x, c whatever. I don't know which c I would be on. I don't know, c sub, I'll just say, what is it going to be? 2k plus 1 or something. 2k minus 1 plus 1. I don't know, but you get the picture, right? So see, I'll just say 2k plus 1 cosine of beta x plus c sub 2k plus 2 sine of beta x. Okay. So in other words, it works just like the repeated real roots. Every time you have an additional one, you just tack on an x and rewrite the thing. Okay, so we want to look at some examples of these guys in context here. So higher order ones, all right, so number 9, let's take a look at that one. We have y triple prime minus 9y double prime plus 15y prime plus 25y 0. Auxiliary m cubed minus 9m squared plus 15m plus 25 is 0. Generally, what I have to do is long division or synthetic division. So I'll guess at a root, like maybe it's 2. So this would be 8. If you plug in 2 and it equals 0, then it's a root, right? So 8 minus 36 plus 30 plus 25. Is that going to work? I don't think sure. You could try all kinds. -1 is probably going to work. One way to do it, one trick to do is just take 25 and use any divisors of it. So plus minus 1 is usually where I start for roots, and then plus minus 5, and then plus minus 25. There's like a, and probably in pre-calc they taught you how to do that, finding rational roots. It had to do with the ratio of the last term and the leading coefficient. But usually if I just try plus or minus 1, it works. And if I get in real trouble, I'll just go to Wolfram Alpha and have them factor it for me. Okay. I probably wouldn't give you anything that's too difficult on a test, right? But anyways, let's try -1. I'm kind of looking at the answer and I know it's going to work. So how do I check to see if it works? So you use the opposite sign of that thing, and then you plop in the coefficients 1, -9, 15, and 25. Bring down the 1. 1 times 1 is 1, so -8. -8, that's going to be 7. That one doesn't work. You have to get a 0 ending up at the end. So let's try -1. 1, -9, 15, 25. Okay. So you bring down this guy, and then -1 times 1 goes here, right? And then you add the column, so you get -10. And then -1 times -10 is +10 that goes there. So you get 25. And then -1 times 25 is -25, so you get 0, so that one works. So as a real root, how does this work out? I'll have m minus -1, and then these guys are the coefficients of kind of the remaining part of the polynomial, right? So it'd be m squared minus 10m plus 25 equals 0. And then I think I might be able to factor this. So I'll have m plus 1 times m minus 5 times m minus 5 equals 0. So my roots, -1 and then 5 is repeated. So my general solution, y, will be c1 e to the negative x plus c2 e to the 5x, and then that one's repeated, so c3x e to the 5x. Okay, let's try another one. See, this one looks kind of nasty, this number 13. So we have 16, let me just put the fourth derivative of y plus 48. Be a little careful with the variables. Every once in a while they'll try to trick you. And like number 10, everything's in terms of t. And I kept putting in x, and I couldn't figure out what was wrong for like ever. Okay, so just be very careful about your variables. Anyways, number 13, we're just in terms of y's and x's, but y, second derivative plus 36y equals 0. So my auxiliary equation, 16m to the fourth plus 48m squared plus 36 equals 0. You could factor out of 4, it looks like, so 4m to the fourth plus 12m squared plus 9 equals 0. And then I'm probably going to be able to factor this thing, so 2m squared plus 3, and then 2m squared plus 3. So this is one where you have repeated imaginary roots. You can get the roots just by setting these things equal to 0. So 2m squared plus 3, you don't have to do a quadratic or anything, equals 0. So 2m squared equals negative 3, so m squared equals negative 3 halves. So m equals plus or minus root 3 halves I, which of course is plus or minus root 6 all over 2I. And then you have this 2m squared plus 3 again, right? So you're just going to get those same roots. In other words, you get 2 repeated roots, imaginary roots. The 0 plus root 6 over 2I, and the other one is 0 minus root 6 over 2I. Okay? So our general solution, y, is going to be e to the 0, right? Because the alpha is technically 0. As you see, there's 0 there, so it's alpha plus or minus beta I, right? So it's e to the 0, which is 1, times c1 cosine of the square root of 6 over 2x plus c2 sine of square root 6 all over 2x. And then plus, then you have to multiply the terms by x, right? So you just sneak in an x, a factor of x. The e to the alpha, again, is e to the 0, so that would just be 1. And then you get c3, I'm going to distribute the x, cosine of root 6 all over 2x plus c4x sine of root 6 all over 2x. Okay. So initial value problems in here are pretty nasty sometimes. Again, number 16, be aware that you're using a different variable. Also, let's look at number 16. So I have u to the fifth derivative plus 3, u fourth derivative minus 2, u third derivative minus 6, u second derivative plus u derivative plus 3, u equals 0. The auxiliary, m to the fifth plus 3m to the fourth minus 2m cubed minus 6m squared plus m plus 3 equals 0. I bet the root is probably going to be negative 1 or 1. Just looking at how all the small terms are. So if you put in 1, you get 4. Over here is 4. That's 8 minus 8. So if 1 is a root, you can just look at it and know that's going to work. Let's say you couldn't figure it out, though. So what do? Well, you can just go to Wolfram. And Wolfram will automatically factor these things. So you just write factor, and then type in whatever thing you're trying to factor. So m, in this case, m to the fifth plus 3m to the fourth minus 2m to the third minus 6m to the 2 plus m plus 3, and just factor it, So you should be able to do these without help to a certain extent. If it's really ugly and nasty like this one, I would just go ahead and use Wolfram. I'm not likely to give you a degree 6 differential equation with order 6. It's probably not going to happen. So, in those cases, rather than killing yourself, just go to Wolfram Alpha, and it'll factor for you. Okay, so there it is. Our roots, -3, there's 2 1s, and then there's 2 -1s, okay? So our general solution, c1e to the -3x plus c2e to the x, and then that was repeated, so you need c2xe to the x, and then plus c3, all the constants are different, even though I keep screwing that up, c4 e to the -x, the first one, and then plus c5, it's repeated, so you tack in an x, e to the -x. That should be our solution. Let's see if that's what I got. Of course, write it with r, don't write it with x, or it will mark it wrong. It's got some nasty ones with, see if there's anything else in here we haven't really talked about. I really hope that'll get you through the homework. Maybe I should do one more. Let's do one more. I don't know which one. So we did that one. That one's nasty enough. Sure, let's do one of these initial condition problems. So number 19 maybe looks kind of nasty. So y triple prime plus 18y double prime plus 81y prime is 0. Initial conditions, y of 0 is 0, y prime of 0 is 1, and then y double prime of 0 is -2. Yeah, I apologize on behalf of the computer for all these nasty answers. They just do not care. Anyways, auxiliary m cubed plus 18m squared plus 81m is 0. M can be factored, so you got m squared plus 18m plus 81 is 0. And that looks like a perfect square trinomial, m plus 9 times m plus 9. So our our roots are 0, -9, -9 repeated. So it's c1 e to the 0, but e to the 0x, right? But e to the 0x is just e to the 0, which is 1. So we just get c1. And then plus c2 e to the -9x. And then repeat, so you tack in an x, e to the -9x. Then I need to get the derivatives and start using the constants to get all the c values. Okay. All right, so let me get the derivatives. Y prime is c1 is 0. We get -9 c2 e to the -9x. I got to do a product rule on the last guy, so it's going to be c3 e to the -9x minus 9 c3 x e to the -9x. Can you combine anything? No. Let's get this next derivative. So I get 81 c2 e to the -9x plus, minus, it's because of the chain rule. So minus 9 c3 e to the -9x. And then I got to do a product rule on the last guy. -9 c3 derivative of x is 1, e to the -9x. And then plus 81 c3 x e to the -9x. Okay, so y of 0 is 0, so plugging that into this equation, I get 0 equals c1 plus c2, right? And then c3 times 0 is times e to the 0 is just 0. Okay, so next guy, plug in y prime of 0 is 1, so I get 1 equals -9 c2 plus c3, and then minus 0. Finally, y double prime of 0 is -2. So I get -2 equals, let's see, 81C2 minus 9C3 minus 9C3. So that'd be minus 18C3. I forgot to combine these like terms. So let's just put 18 minus 18C3, and then the last guy is 0. Okay, so I got a little system of equations, 3 unknowns. I'll note here that C1 is just equal to negative C2. I could use these second equations and solve them. Okay, so get these guys as a team. Multiply the first one by 9. So I get 9 equals negative 81C2 plus 9C3. And then I have negative 2 equals 81C2 minus 18C3. Add those column-wise, so I get 7 equals 0 minus 9C3. And then I get C3 is negative 7 ninths. So plug that into the one of the unused equations. I'll just pick this guy here to solve for C2. So I get 1 equals negative 9C2 plus, in this case, minus 7 ninths. Add 7 ninths to both sides, so I get 9 ninths plus 7 ninths equals negative 9C2. Well, I get 16 ninths equals negative 9C2. So C2 looks like it's going to be negative 16 all over 81. And then C1 is just the negative of C2. So from here, I can see that C1 must be 16/81. Does that even look familiar? Just cheat a little bit. Yeah. So my final solution then, going back to the y prime above, or sorry, the y equation, the general solution, y will equal C1 16/81 plus C2, which is just the negative of that, so that would be minus 16/81 e to the negative 9x, and then plus C3, which is minus 7 ninths x e to the negative 9x. And that letter be your solution. Okay. All right, so a lot of work here. You're going to get better and better at taking derivatives and eventually also doing more and more integrals. And hopefully that will get you through the homework. And as usual, thank you for watching, and we'll see you next time.